Good morning. Oh. All right. I was a little bit late getting that link posted. That's my fault. So I'm going to give just a few minutes for folks to show up, and that means we'll run a few minutes over at the end. So apologies in advance for that. The plan for today is to talk more about min-max problems, maybe do a few examples from your homework, and try to get you guys comfy for where we're going next. Here it is. So while I'm waiting for folks to show up, let's see. Yeah, we could talk about L'Hopital's rule, curve sketching. Yeah, so where do we hit that? So 4.5. It is. I think I want to talk about that shit today anyway. Even though it's not an official part of what we're doing this week, it's still the right thing to do. I don't think I have any problems of that nature in here. Critical numbers, critical numbers. Absolute min, absolute max. Yeah, okay. We'll do a few find critical numbers. Yeah. Oh, yeah, that's fine. That's just all right. It looks like most folks are here. So let me fire up the .cam software. We'll go ahead and get started. So there we go. All right. Today I want to talk more about section 4.1. And I want to talk a little bit about some of the material that is officially stuff we're covering next week, but it's not the sort of thing that I give you a lot of homework on. So there's a few concept heavy sections that are officially a part of next week's material. Here, I'll swap over to the syllabus and show you what I'm talking about. So right now we are officially like right here, which is supposed to be from a couple weeks ago. So we're a little bit behind. That's okay. Next week, we're going to cover mean value theorem, L'Hopital's rule, and curve sketching. Mean value theorem is a cool theorem, but there's not a whole lot in the way of like skill building there, right? So there are problems that I can design around the theorem that force you to like solve a problem having to do with the mean value theorem, but it's not one of the main skills that we're trying to practice in this class. However, curve sketching is the exact opposite. It's very light on theorems and very heavy on skills that we're trying to build. So next week, I would like to be able to focus pretty much exclusively on curve sketching, which means I'd like to talk a little bit about these things. L'Hopital's rule is something that's going to have to show up in the homework next week because it's something that does require practice. But really, this is the big thing. So I want to cover a little bit of MVT. I want to talk about this shit with you guys this week so that we don't have to spend too much time on it next week. And then I also want to show you a little bit of this stuff because it's hugely important. This right here is what all of this is building to. Getting to a place where you can draw really good graphs of functions by hand, no graphing calculator, no point plugging. By using information from the first and second derivative of a function, you can draw excellent graphs. So I'm going to connect the curve sketching portion to what we've been doing. And I'm going to talk to you a little bit about the mean value theorem. And that way next week we can focus on L'Hopital's rule and curve sketching and also kind of get you ready for exam 2. Because exam 2 really should have been this week. but it's okay, it's all right. I've got a bunch of extra time built into the syllabus towards the end here, and this is definitely meant to be a rough outline. It's okay if we deviate a little bit. So the plan is definitely still to have the exam be the week of the 20th, which is going to make us rush a little bit towards the end here, but it'll be all right. We're gonna work this in today. So today, more min-max stuff, a little curve sketching, and a little MVT. That's the plan. Okay, and then a reminder. Exam 2 is going to be on the week of 7/20. I want to remind you a few of the main things from last time. To find extrema, and remember, extrema is the word for mins and maxes, local or absolute. To find extrema, we set f primed equal to 0. Record the critical numbers. And these are places where f primed is 0 or f primed is undefined. And then compare y values. Right, that was the basic 3-step algorithm that we discussed in class last time. I hinted at something there because your critical numbers can give you local extrema or absolute extrema, like a local max or an absolute max, local min or absolute min. And this business of just comparing the y values at the end is a great way to find your absolute max and your absolute min. But it doesn't really help you identify a local max from a local min. A local max is going to be a place where f primed is 0 usually. A local min is going to be a place where f primed is 0 usually. And so there's no obvious way to detect, right? You could have a local min that's larger than a local max. So the question I would like to ask, let's draw it like this. All right, this local min is bigger than this local max. These are all places where f primed is 0. So how can we tell a local min from a local max? Because it's possible that the local min has a larger y value than the local max. All right, this sort of shit can totally happen. And the answer there comes from something that's related to curve sketching. Comes from something that we're going to talk about a lot more when we get a little bit deeper into chapter 4.
I have like a little thing in my brain. Does it have to do because we're reading the graph from left to right? So the first one is a local min, while the other one is a max because reading it from left to right, it's rising.
That's the idea. It's to do with the rising and falling. It's to do with being increasing and decreasing. Yeah. So there is a connection there with the left to right nature of how we read the graph. But it's a little bit more subtle than that, right? Just because this occurs to the left of this doesn't guarantee that this would be a local min and this a local max. For example, this is a local max that occurs to the left of this local min. But it does have to do with decreasing, increasing, decreasing, increasing. So
wouldn't it be related to the way the line approaches the minimum or maximum from each side?
it
I guess-
is.
sorry.
Yeah, that's the idea, right? So if I look nearby here, the tangent line has a negative slope. And if I look nearby on the right-hand side, the tangent line has a positive slope. And the only way for that to happen is if we rolled through a min here, right? If you're decreasing, 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 0, increasing, 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 that means that you had to have rolled through a min. The only way to go from decreasing to increasing in a smooth fashion is if you rolled through the bottom of a valley. And that's the main thing I wanted to convey to you guys. So I wanted to look at some of the examples that we're playing with right now, and I've got some of them up in the homework here. We'll solve the question as it's given, which for this week is just to find, well, let's see. So we have something here that's a little more exciting. Critical numbers, abs min, max. Yeah, let's look at one or two of these guys and see if we can't sort out the local extrema from the absolute extrema. Now these problems are designed to be nice and straightforward for where we are, but I think I'm gonna turn off my screen share for just a minute so I can verify. I don't want to spoil it for you. Okay, yeah, this looks good. Okay. So we'll come back here and turn the screen share back on. I want to take a more detailed look at this problem, right? Number 18. So here you're just asked to find the absolute min and the absolute max for this continuous function on this closed bounded interval. And to do that, we just have to run through that 3-step process. But this guy also has some local extrema. So I want to identify those local extrema and talk a little bit about how you can tell the mins from the maxes, because I feel like that's the right thing to talk about here. So the place where we're going to talk about this again is going to be in section, I think 4.4, something like that. So we're kind of jumping around a little bit. Summary of curve sketching, 4.5. This will be it. Derivative affect the shape of the graph. Oh no, 4.3. Yeah, this is it. Okay, yep. So we're going to talk a little bit about 4.3 right now. We're going to do kind of an intro to 4.3, and then we'll do a little intro to 4.2, and that will be our wrap up here. So something we've said in the past. If f primed of x is negative, then f of x is decreasing. And if f primed of x is positive, then f of x is increasing. And then observe at a local min, f primed of x must go from negative to positive, because f of x goes from decreasing to increasing. And at a local max, f primed must go from positive to negative, because f of x has to go from increasing to decreasing. This is what's called the first derivative test. So if I wanted to know whether this point right here is a local min without having the graph, what I would do is first I find all of these critical numbers by setting f prime to 0, but then I look just to the left of this point and just to the right of this point. Since f primed here would be negative and f primed here would be positive, I know that I went from decreasing to increasing, which means I had to roll through the bottom of a valley. I had to turn around. I was going down, 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 turn around, go up, 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 up. That means that was a valley. So that was a local min. And similarly here at this critical number, I know that I went from increasing to decreasing, because if I look at f primed right over here, it would be positive, and f primed over here would be negative. That means f went from increasing to decreasing, which means I went over the top of a hill, right? If you're going uphill, 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 downhill, 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 that means you just rolled over the peak of a hill. You just went through a little local max. So let's take a look at that problem with this shit in mind. And not only are we going to find the absolute min and absolute max like the problem asks us to, but we're also going to characterize the local min and local max. So I'll write this down. This is homework 8, number 19. Find and classify extrema for f of x equals 6x to the 4 minus 8x cubed minus 24x squared plus 1 on the interval -2 to 3. All right. So you may remember in your pre-calculus class when you talked about solving nonlinear inequalities, where you had to make a number line, you chop things up into regions, you test a point from each region, and then you assign like a plus or a minus to each region. This is that same shit, right? Now we are to the place in calc where that skill becomes relevant. So this is where we're going to apply that. First, find the critical numbers. All right, these are numbers where f primed of x is equal to 0 or f primed of x is undefined. So I need to take f primed. F is a polynomial, so f primed will be a polynomial, so there's no place where it's going to be undefined. If I differentiate this piece, I get 24x cubed. If I differentiate this piece, I get 24x squared. If I differentiate this piece, I get 48x. And if I differentiate the 1, I get 0. So this is f primed. I can factor out a 24. I can factor out a 24x, in fact. And what's left will be x squared minus x minus 2. And x squared minus x minus 2 also factors, right? That is x plus 1 times x minus 2. So my critical numbers this guy, if I set him to 0, will give me -1. This guy, if I set him to 0, will give me 0. And this guy will give me 2. So those are my critical numbers. Now, if I'm just looking for the absolute extrema, remember my second step here is to compare the y values at the critical numbers and endpoints. So the endpoints here are x equals -2 and +3. So let's go ahead and do that. F of -2 is 6 times -2 to the 4 minus 8 times -2 cubed minus 24 times -2 squared plus 1, which is what? I'm going to be lazy here. This is 65. The next one I need to look at if I'm going in order from left to right is f of -1. That's one of my critical numbers here. So I'll swap these for -1s. That's -9. F of 0, that's easy, that's 1. What was my next guy? 2 and then 3. So f of 2, swap in 2's here. We get -63. And finally, f of 3, that was my right endpoint. So I'll swap in some 3's here. That's 55. Okay, so I have all these y values. F of -2 is 65, f of -1 is -9, f of 0 is 1, f of 2 is -63, f of 3 is 55. So my absolute min for f of x on the interval -2, 3 is, which one of these is the smallest? This, no, this, no, no, no. Yes, it is -63. And it is attained when x is equal to 2. The absolute max for f of x on -2, 3. What's the absolute largest value here? It looks like 65. And it is attained when x is equal to -2. Okay. This is all well and good. So this would be step 3 here. Sorry, I kind of crowded this in. But what about these other guys, right? So only 2 of these were relevant to the problem as it was stated, because they just asked for the absolute min and absolute max. So we know that something else has to be going on at these other places, right? At -1, 0, and 3. what's going on there is local extrema. And I would like to know, so what's going on at the other critical numbers? So what were my other critical numbers? -1 and 0, right? To answer this question, we need to make a number line for f prime. So here, I'm going to place all of my critical numbers, which are -1, 0, and 2. The endpoints are not critical numbers. They're just useful for finding the absolute min and the absolute max, because remember, it's possible for a function to attain its absolute min or absolute max not at an interesting like point on the graph, but at an endpoint if you're looking on just a closed bounded interval. If you remember polynomial end behavior from your pre-calculus class, looking back at this guy, f primed, I see that f primed is an odd degree polynomial with a positive lead coefficient, which means that the end behavior for f primed positive lead coefficient, odd degree, must go down on the right and up on the left. In particular, that means f primed is negative over here. And then this root at -1 is coming from this odd multiplicity factor. Right? This x plus 1 factor is what gave me this critical number. And since it is an odd multiplicity factor, f primed will change sign there. Same is true of these other two factors. They're also both odd multiplicity factors. So every time I jump over an odd multiplicity factor, f prime will change sign. So it'll be negative here and it'll be positive here. You could also test a point from each region. That's another option to fill out this number line with the minus or the plus. This means that f will be decreasing here, increasing here, decreasing here, and increasing here. So that tells me what's happening here at -1. If f of x is decreasing, decreasing, decreasing until we get to -1 and then increasing, 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 that means right here, there's got to be a local min. And if we're increasing, 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 and then decreasing, 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 that means that right here at 0, there's got to be a local max. And then again over here, we're decreasing, 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 increasing, increasing, increasing. That means there is a local min. So now that I have all this information, I could draw a really good graph of f. Let me try to do that. So where were my y values? The local min at -1, this was -1 comma 9. -1 comma, sorry, -9. The local max at 0 was at 0 comma 1. And the local min at 2 was 2 comma -63. So here I'll mark -1. Here's like 0 comma 1, And 2 comma negative 63 would be way the fuck down here. We're just going to call this negative 63. And I know what the behavior nearby there looks. Negative 1, what was the y value there? Negative 9. So we'll call this negative 9. I know that at negative 1 comma negative 9, I had a local min. So locally, the behavior here looks like this. I know that at 0 comma 1, I have a local max. So locally, the behavior there looks like this. And I know that at 2 comma negative 63, the behavior looks like this. So the graph of f has to look something like this. Right? This is the basic idea. Now imagine that you knew exactly where these x-intercepts were. Then you could draw a really good picture of the graph of f. And nowhere in here did I ever have to resort to any graphing utility. Nowhere did I need any calculator or Desmos or anything to do this. So this is the beauty of using the first derivative to get a good graph, right? This is really the main point of the first 2/3 of this class. It's that you can find where a function is increasing and decreasing by finding out where its derivative is positive and negative. And once you know where a function is increasing and decreasing, you can identify the local extrema. So this is the main point. Now, how do we connect that to what we're doing here? Well, we can just extend the solution to this problem a little bit. So I found the absolute min and absolute max. I've also identified the local mins and local maxes, right? So the absolute min was at 2, and the min value was negative 63. The absolute max was at negative 2, and the absolute max value was positive 65. But then in addition to that, I had a local min at negative 1, negative 9, a local max at 0, 1, and then this guy, who was my absolute min, turns out to also be a local min. And we can verify with Desmos. No harm in that. Scale my y values. Right? You see here, compare this to this. The basic shape is right. I have mins and maxes at the right place. The end behavior is right. The only difference here is that I rescaled my y-axis a little bit. This should be, I guess, further up here if that's supposed to be negative 63, but I was being a little sloppy. You see we've got a really nice graph. Getting all the important shit right. Where are we increasing? Where are we decreasing? Where are their mins? Where are their maxes? The only thing that I didn't take time to do here is to find these x-intercepts, which for this function would be a little bit tough because the polynomial that we're graphing here is a degree 4 polynomial. But this is where we're going, right? So think of this as your little intro to section 4.3. Getting to a place where you can write this number line for f primed, which tells you where f is increasing and decreasing, will tell you whether your critical numbers are local mins or local maxes. That's really useful stuff. And this is what we will be focusing on primarily next week. Questions on these number lines? Was anybody able to follow how I filled out this number line for f prime? Do you guys remember doing this stuff in pre-calc? Where you had to make these? So back then in pre-calc, I would ask you to solve an inequality. I would say, solve for me, you know, f of x is greater than 0. And you would make this number line, and then you would say, oh, well, this region and this region, that's where f of x is greater than 0. Now I'm doing the same thing, but I'm doing it with f primed, because f primed being positive and negative corresponds to f increasing and decreasing. So solving nonlinear inequalities, that chunk from pre-calculus, hugely important here. We'll go over this in detail next week. I just kind of wanted to get you ready for it. I wanted to prime you for it, to make a bad pun. But before I talk about the mean value theorem, I want to solve one more of these problems from your homework, just to kind of get you guys a little bit more comfy. I won't go and do the number line and the local min, local max thing for this one. So this next guy is going to be just a little bit more rehearsal for what you're supposed to be working on right now. That was number 19. I think for this next guy, I'd like to look at something a little bit more complicated. Let's do this. Let's do number 22. Oh shit, I'm gonna swap the t's for x's because I already wrote f of x. Okay. So I'd like to find the absolute min and absolute max for this function on the interval 0 to pi over 2. Again, this is a continuous function on a closed bounded interval, so I know that there will be an absolute min and an absolute max. They could be coming from local mins and local maxes on the interior of this interval, or they could be coming from the endpoints. The procedure is still the same. First, I find the critical numbers. Here, that's going to involve taking the derivative and then solving a trigonometric equation. So the derivative of cos is negative sine, so this will be negative 4 sine x plus 2 times, and now I need to differentiate the sine of 2x. That's a chain rule thing, so I'll differentiate the outer function first, derivative of sine is cos, and then I multiply by the derivative of the inside. So here is f primed. I can rewrite that as negative 4 sine of x plus 4 cosine of 2x. And then factor out, let's factor a negative 4. This will be sine x minus cos 2x. And I want to set this to 0. Now, setting this to 0 as it is a little bit complicated. So before I do that, I'm going to use a double angle identity for cosine. Cos 2 theta is the same as cos squared theta minus sine squared theta. So this is negative 4 sine x minus cos squared x minus sine squared x. Close and close. All right, so that big paren at the end closes the big paren here. I'll distribute this negative. And my goal is to figure out where this apparatus is equal to 0 So there's one more thing I need to do. If I wanted to solve this equaling 0, I would like to get rid of the cosine here. I'd like to get everything in terms of sine. So let me step aside here. F primed of x will equal 0 if and only if 0 equals -4 times sine squared x plus sine x minus cos squared x. You can divide both sides by -4. And then from your trigonometry classes, you should remember how to solve equations like this. If you don't, that's forgivable. You need to replace this by his Pythagorean equivalent and then factor the resulting quadratic. So this is the same as sine squared x plus sine x minus 1 minus sine squared x. I'll distribute this negative. So this will become -1 plus sine squared x. So I'll have altogether 2 sine squared x plus sine x minus 1. All right, and I want to solve this thing is equal to 0. And the idea here is that if you had, instead of sine x, you had just like u, then this would be like 2u squared plus u minus 1. So this would be 2u squared plus u minus 1. This can be a useful trick for helping you factor. So if I want to factor this using the AC method, I take this number and this number. That product is -2. So I need to find two numbers that multiply to -2 and add up to +1. Those are going to be +2 and -1. So I can rewrite this as 2u squared plus 2u minus u minus 1, and then factor by grouping. So that's 2u minus 1 times u plus 1, which is 2 sine x minus 1 times sine x plus 1. So there is my derivative set to 0, factored nicely. So I'd say therefore, f primed of x equals 0 if and only if 2 sine x minus 1 equals 0 or sine x plus 1 equals 0. This first guy tells me sine x is equal to +1/2. This second guy tells me sine x is equal to -1. And remember, I'm working on the interval 0 to pi/2. So I want to find any solutions to these equations between 0 and pi/2. Where is sine x equal to 1/2 on that interval?
pi/6.
Good. And where is sine x equal to -1?
Minus pi/2.
Yeah, so we could write this as like -pi/2 or 3pi/2, but none of these are in the interval 0 to pi/2. So remember, I'm trying to solve this on the interval 0 to pi/2. So really my only critical number in that interval is pi/6. 6. So the critical numbers for f are just x equals pi over 6. All right. So my next step is to compare the y values at the critical numbers and endpoints. So f of 0, 0 is my left endpoint. That's 4 times the cos of 0 plus 2 times the sine of 2 times 0. Cos of 0 is 1, sine of 0 is 0, so this is 4. F of pi over 6 is 4 times the cos of pi over 6 plus 2 times the sine of 2 times pi over 6. Sorry, this is a 6. The cosine of pi over 6 is root 3 over 2. And the sine of pi over 3 is also root 3 over 2. So this is 4 square roots of 3 over 2 plus 2 times the sine of 2 times pi over 6. So 2 times pi over 6 is pi over 3. The sine of pi over 3 is root 3 over 2. So this is plus 2 root 3 over 2.
Can you zoom in just a little bit, please?
Yeah, sure. Sorry, the camera's having a hard time focusing today. So this guy, cosine of pi over 6, is root 3 over 2. So that's this piece. This guy, the inside of the sine function there is 2 times pi over 6. That's pi over 3. And the sine of pi over 3 is also root 3 over 2. So we've got 2 times root 3 over 2. This whole piece here is just the square root of 3. This piece here is 2 times the square root of 3. So I've got altogether 3 square roots of 3. And then finally at my left endpoint, f of pi over 2, that's 4 times the cos of pi over 2 plus 2 times the sine of 2 pi over 2. The cos of pi over 2 is 0, and 2 pi over 2 inside here is pi. The sine of pi is also 0. So this is 4 times 0 plus 2 times 0, that's 0. So these are my y values, 4, 3 root 3, and 0. Square root of 3, this guy might not be super easy to compare. I know it's bigger than 1, smaller than 2, but that's not quite enough for me to say whether 3 root 3 is bigger or smaller than 4. So you'd be forgiven if you wanted to use a calculator here for a minute. I think 3 root 3 will be bigger than 4, but just to be sure. Yeah, it's about 5. 5.19-ish. So now I compare and write down my absolute max. So my abs min is coming from which point? Well, it's coming from pi over 2 comma 0. So I would say the min value is 0, and it is attained when x is equal to pi over 2, and my abs max coming from the point pi over 6 comma 3 root 3 So the abs max is 3 square roots of 3, and it is attained when x is equal to pi over 6. Okay, so that's this problem solved. It's not too bad. Definitely the hard part here is solving the trig equation, right? You take f prime and you set it equal to 0. That gives you a trig equation that's a little tough to solve. So you have to remember all those skills from your trigonometry class. You know what they say, Calc 1, make sure you remembered your algebra and your trig. Calc 2 will make sure you remembered your Calc 1, and so on. Each next math class kind of makes sure that you remembered the previous.
Excuse me, sir.
Yeah.
Yeah, 4 of 0 equal to 4, so I think 4 is greater than 3 root square 3.
Yeah, so that's what I had to check there. 3 root 3 is about 5.19, which is bigger than 4.
Okay.
Yeah, so I had that doubt.
Okay.
I wasn't sure whether this or this was larger. That's why I pulled up the calculator here real quick. But 3 root 3 is
All right.
a little bigger than 4. Reasonable question.
Thank you.
Of course. Let's take a quick look at this graph. So this was 4 cos x plus 2 sine 2x. And I was restricting my attention to 0 is less than or equal to x is less than or equal to pi over 2. So that's this tiny little piece here. And we're seeing what we think we're going to see. So pi over 6, comma, f of pi over 6 is this point, my abs max. No? And then my absolute min was at the end point. All right? So this absolute max is also a local max. This absolute min is technically also a local min, but he's not coming from a critical number, he's coming from the endpoint. And the endpoint on the left didn't contribute anything. Is everybody able to follow how we did this? So we took the derivative, we set it equal to 0. That's how we found this guy in the middle. And then we compared that against the values of the function at the endpoints. This guy turned out to have the largest y value, and this guy at the endpoint turned out to have the smallest y value. So I would like to take a second here to answer any questions you guys have about this. There was quite a bit of work here. And most of it came from solving this equation f primed of x equals 0. So we took f primed, we tried to simplify it. We set that equal to 0. And then in order to solve that equation, we had to use another trig identity, and then substitute, factor, and then we took each of these factors and set them to 0 on their own. That first guy, he did give me something useful. That's where my absolute max came from. The second guy, he had a solution, but none of those solutions were in the interval that I was asked to work on. I was asked to pay attention just to the interval 0 to pi over 2. And neither of those solutions were in that interval. So my only critical number on that interval was this one. But I think definitely the hard part here is this, right? Is solving this equation, f primed equals 0. So questions here. I'm happy to hang out here for a second and answer any questions. It's totally understandable if you've forgotten how to do some of this stuff down here. What would we like to look at?
Confirmation cos squared x equals 1 minus sine squared x.
Yep.
There was another one we used, wasn't there? Oh,
Yeah, so the cos squared equals 1 minus sine squared. We use that here.
Mhm.
And also up here, we used cos 2x equals cos squared x minus sine squared x. That's the double angle formula for cosine.
Yeah, thank you.
Okay. Yeah, those are the two trig identities we needed to solve that equation. What else are we wondering about as we look at this problem? Would we like to do one more like this?
Yeah, please.
Okay, let's do it.
And you made u equal to sine x.
Yeah, down here, in order to help me factor this, I made u sine x. That makes it just easier for me to see how to factor that. Some people like to factor them straight from here. And that's fine. If you can jump from this line to this line without the in-between stuff, I applaud you. You're better at factoring than I am. But for me, it's helpful to rewrite this as 2u squared plus u minus 1. That helps me see how to factor. So let's come over here and find one more problem that we can play around with. We did one like that. Find the critical numbers for this. Find the critical numbers for that. Let's look at 15. 14 and 15, both kind of interesting here. Both of these just say find the critical numbers. I'll let you guys choose. Do we want to do 14 or 15? This is kind of a weird quotient rule. This is kind of a weird product rule. Any strong feelings one way or the other?
Well, let's try 14 then.
All right.
Which one do you think is better?
You know, I don't have a preference between them. So let's take a look at 14. Okay. So I want to find the critical numbers for this function. Here my variable is y, which means I need to take the derivative and set the derivative equal to 0. Find any place where the derivative is equal to 0 or undefined. It might be useful to find the domain of this function. So let's see, can I factor that bottom? Are there two numbers that multiply to 9 and add up to -3? Well, 9 is 3 squared, so I don't think so. So that denominator doesn't look like it's going to factor. So let's just jump in and start differentiating. G primed of y, remember my rule, it's low d high minus high d low over low low. So that's the bottom times the derivative of the top. The derivative of the top is just 1 minus the top times the derivative of the bottom. The derivative of the bottom is 2y minus 3 all over the bottom squared. And I can clean this up a little bit. I'll distribute over here. So this is 2y squared minus 6y minus 3y plus 9 . So what do I get? My y squareds, I've got 1y squared here minus 2y squared there. That's negative y squared I've got minus 3y here, minus negative 6y minus 3y. That's going to be plus 6y. And then I've got plus 9 minus 9. So that's 0 all over y squared minus 3y plus 9 all squared. So if I want to set this equal to 0, what do I do? I set the top to 0, right? This big fraction will be 0 if the top is 0 and the bottom is not. I can factor a y, or even a negative y if I want to. So g primed of y equals 0 if y is 0, that's coming from this guy, or if y is 6, that's coming from this guy. So those are my two critical numbers. They're 0 and 6. And that's all we were asked for, is just find the critical numbers. So you take the derivative, set it equal to 0. The only other thing you got to watch out for is places where the derivative is undefined. That would be somewhere that this bottom is equal to 0. But the denominator here is the same as the original denominator all squared. So anything that would make this denominator 0 would also make this denominator 0. So I'm not going to get any critical numbers from setting this bottom equal to 0, because those numbers are necessarily not in the domain of the original function. So remember what the definition of a critical number is. It's anywhere that the derivative is 0 or undefined, but also in the domain of the original. So this is it. My critical numbers are 0 and 6. We can look at the graph. I'm going to use the variable x here. See if we can get a decent picture of this. Ooh, not looking good there. All right, let's see. Oh, it looks like I need to bring my y scale in actually. Let's go like something like this. There we go. All right, so the critical number at 0 is here. The critical number at 6 is here, all right? And you see that one of them is a local min. And the other one gives us a local max. Neat stuff, right? So finding critical numbers is the key step to finding minima and maxima. And that's why this is what you're doing here on in this function and in this homework. If I was looking for absolute mins and absolute maxes, if you look at this whole graph, you see, oh, well, this guy down here, not just a local min, but is also an absolute min. And this max here isn't just a local max, he's also an absolute max.
I have a really quick question.
Sure.
So looking at the graph,
Mm-hmm.
I noticed that you put like 6 comma f of 6.
Mhm.
But the f of 6 being the y value doesn't actually show 6 on the scale. So what is f of 6? Like, I don't know if I'm missing something.
F of 6 is the number you get out when you plug 6 in for x here. So the x value here is 6. You see that, right?
Yes.
F of 6 is the y value at this point on the graph. So f of 6 is right there. It's 0.111111111, which is, I think, 1/9. So if you plug 6 in here, you'll get 1/9 after you simplify.
Okay, thanks.
So
So
remember,
is that like,
every point along the graph of f of x is always some number, comma, f of that number. Like f of 10 doesn't have y value 10. The y value there is like 0.8 or 0.08, right? So the y value at any point along the graph of f is what you get out when you plug in that x value. So f of -4 is -0.118, because if you put -4 in here for x, you would get -0.118 out.
so is that the concept of like the idea of the prime when you're plugging it in next to the x value?
No, no real prime thing there. It's just the idea of what is the graph of a function. So the graph of any function is the collection of all the points x comma f of x. So right here, I can see f of -6. If I can get it right there, f of -6 is -0.1429. Right? That means if you plugged -6 in for x in the formula for f of x, you would get -0.1429 out.
Okay, thank you.
And then Tybee asked a question in the chat. So we're only concerned about the numerator. Let's come back here. So when I set this thing equal to 0, you may remember this from your study of rational functions in pre-calculus, this whole thing, this big fraction, will be 0 if the top is 0. So it's true that when I'm trying to figure out where is this equal to 0, I only care about the numerator, right? What sort of fractions are equal to 0? Well, 0/5, 0/10, 0/pi. Those are all 0. So if the top is 0, then the whole fraction will be equal to 0. That's the idea. Okay. Any other questions about how we found these critical numbers or how these critical numbers relate to this graph? All right. Let's take a quick look at number 15. These both look like good problems worth spending some time on. We want to find the critical numbers for f of x equals x to the 4/5 times x minus 5 all squared. So I'm going to take f primed. Here, this is a product rule thing, so I'll differentiate the x to the 4/5. If I subtract 1 from the power of 4/5, I'll get -1/5, and I'll leave the other guy alone. Now I'll leave the x to the 4/5 alone and differentiate the other guy, which does require a little chain rule thing, but the derivative of the inside is 1. And now I need to set this equal to 0, but this is a little bit weird to set equal to 0 because I've got this negative power here. So this is really 4 times x minus 5 all squared over x to the 1/5 plus 2x to the 4/5 times x minus 5. This is the thing I want to set equal to 0. And in order to do that, I need to write it as a single fraction and then set the top to 0. So I need to have a common denominator. The denominator in this piece is 1. The denominator in this piece is x to the 1/5. So I need to multiply this guy by x to the 1/5 over x to the 1/5. So I'll have 4 times x minus 5 squared plus 2. I'll group these terms, x to the 4/5 times x to the 1/5 times x minus 5, all over x to the 1/5. This piece is 4 times x squared minus 10x plus 25 plus 2 times x to the 4/5 times x to the 1/5 is x to the 4/5 plus 1/5, which is x to the 1. And now I'll distribute everything out. This is 4x squared minus 40x plus 100 plus 2x squared minus 10x, all over x to the 1/5. So if I group my like terms, I have 6x squared minus 40x minus 10x is minus 50x plus 100, all over x to the 1/5. That is my derivative simplified as much as possible. And it's kind of hard to see that it's going to come out that nice from this step, but it does. You just got to be patient with your algebra. Careful with your algebra and patient.
How did you get to that second step?
How did I get here?
Correct. No, just kidding.
So from here to here, I just took this x to the negative 1/5 and moved it downstairs because that power was negative. So he really belonged downstairs.
Okay, thank you. My bad. I
You're
totally
good.
didn't write a negative.
Oh, yeah. So this is a negative 1/5 power because I subtract 1 from the 4/5 power. And then I realize that since this is a fraction whose denominator is x to the 1/5, I need to write this as a fraction with that same denominator. So I multiply by x to the 1/5 over x to the 1/5 to give a common denominator. That brings me to here. And then these two guys, when you multiply x to the 4/5 times x to the 1/5, that's x to the 1. Everything else just comes along for the ride, the x to the 5, the 2, and here I foiled out the x minus 5 squared piece. Here I distribute the 4 and distribute the 2x, and then here I combine like terms. So you're going to want to, this is where your time is going to be spent on these problems, right? Let's be clear about this. The differentiation is not that hard. It's a product rule thing, and hopefully at this point you're pretty good with the product rule. The work is all in this algebra. So take your time and maybe rewatch this video and make sure you're comfy with these algebra steps. There are tricks, BT dubs. If you don't like doing this, this is the straightforward way to do it. There is a trick here that you can employ where you factor out the largest negative power, and that will get you to this a little bit quicker, but I think this is the more intuitive way to do it. So I would recommend just rewatching those steps carefully. Now to find my critical numbers, the reason I wanted to do this, the domain of this original function is all real numbers. He doesn't have any variables downstairs. He doesn't have any variables under a square root or anything like that, which means that now I am going to get a critical number from the denominator. So where is f primed of x equal to 0 or undefined? Well, f prime of x is undefined when x to the 1/5 is equal to 0, which means x is equal to 0. So here I do get a critical number from the bottom. And f primed of x is equal to 0 if the top is equal to 0. So that's 6x squared minus 50x plus 100 is equal to 0. I can factor out, can I factor a 4? No, but I can factor a 2. So that's 3x squared minus 25x plus 50 equals 0. And then I need to find a way to factor this. 3 times 50 is 150. So I need two numbers that multiply to 150 and add up to negative 25. We're a little short on time here. Let's see. Now, can we do this? We can do this. Two numbers multiply to 150 and add up to negative 25. So divisors of 150. It's 2 and 75. 3 and 50. Is 150 divisible by 4? Is it divisible by 5? It is. It's 5 times 30. Oh, this will work. So this is 2 times 3x squared minus 30x plus 5x plus 50. So that's 2 times 3x times x minus 10 plus, oh wait, that's minus, isn't it? Did I fuck up? Negative 30 plus 5. Oh no, that's negative 150. Yeah, no, this doesn't work, sorry. So let me go ahead and hack this really quick. I wrote that down right, yeah, plus 1. 0. So are these numbers nice? 10/3 and 5, yeah. Okay. So these are my critical numbers. 0 from setting the bottom equal to 0, and that's okay because the denominator here being 0 does not take me outside the domain of this original function. And then these guys from setting the top equal to 0. So I'll zoom out so you can see all this. Real quick, let's take a look at this graph and then we will have to end things for today. Let's play around with these scales. Whoa, no. All right, so it's a little bit hard to see. Maybe play with the scales just a little bit more. Let's do like 0 to 10, 20, something like this. So what we've got going on here is we've got a local max here, a local min here, and a local min here at 0. It's called a cusp. Damn it. There we go. All right, so you've got a local max here, a local min here, and a cusp here. And those are coming from the 3 points that we found, the 3 critical numbers. Oh, wait, no, that's not that guy, is it? What was it, templates? What was the other one? Yeah, this is the critical number. It was 5. And what was this guy? 1.429. So I must have goofed up solving this polynomial equation at the end here. But those critical numbers correspond to these points, right? This is the idea. So you find the critical numbers, those will help you find any local mins or local maxes. What I wanted to point out with this example is this guy here at 0 is special. This is a place where f primed was undefined, and that's why you have a cusp there, something pointy, rather than a nice smooth hill or a nice smooth valley. So the critical numbers that come from places where f primed is undefined will give you these pointy cusp things, and the critical numbers that come from f primed being 0 will give you these smooth things. All right, so I am gonna have to stop the video here for today because this is, I got another class to teach. I hope that you feel a little bit more comfortable finding critical numbers and that you can kind of see where we're going with the increasing and decreasing stuff.
Excuse me, sir.
Yes.
I emailed you homework 7, the last 2 questions, 18 and 19, the PDF. So I did many times. I didn't find the answer. I don't know why. So maybe you can check up with me.
Yeah, sure. Give me just a little bit of time and I'll respond to that email. I think I saw it yesterday.
Okay.
I just haven't had time to answer it yet. But definitely.
Okay, thank you.
Yeah, I will, yeah. And then there's some questions here in chat. So a question about test 2. Is test 1 a good representation of what test 2, 3, and the final will look like? Yes. Yeah, so test 2 and 3 will be conducted in the exact same way as test 1 on Canvas, just like that. And the final exam will likely be done that way also. It'll just be a longer test. So the final, remember, is cumulative, covers everything we've learned in the semester. Tests 2 and 3 are not cumulative. Like test 2 will just cover the stuff that we've done since exam 1 until we finish, which is going to be right around section 4.5. And then test 3, again, not cumulative, just covering the last third of the class. But then the final will be cumulative. And they will all be about the same. Yeah, they'll all be on Canvas. They'll all be a mixture of true, false, multiple choice, and free response. And you'll be submitting your work in the same fashion. Any other questions for me before we sign out for the day?
Yes, that's x, bottom left, f prime of x is undefined when x to the 1/5 equals 0?
Right,
That-
so I set the bottom equal to 0 to find out where f primed is undefined. So the bottom is x to the 1/5. So f primed will be undefined if its denominator is equal to 0. Its denominator is x to the 1/5. And then I solve this equation just by raising both sides to the 5th power. So 0 to the 5 is 0, x to the 1/5 to the 5 is x. So this apparatus downstairs will be 0 when x is 0.
Thank you.
Of course. All right, so I am going to go ahead and sign out here. If you have any further questions for me, I'm going to try to hold an office hour. My wife and I have both become a little bit sick, so the office hour may be a little bit short, and I'm sorry for the lack of office hours this week, but I will be there for at least a little bit after I finish up my Calc 2 class. And of course, as always, you can email me if you have any other questions or send me a Canvas message. Please do keep working on the homework. Try to finish up homework 8 over this weekend. That way next week we can focus on the mean value theorem and some applied optimization problems. Those will be the big things. And then we'll be getting ready for exam 2. So next week we'll have MVT, curve sketching, and an intro to applied optimization. You are in the meat of the course right now, so it's very important that you're working hard. You should be spending several hours a day, every day on this homework. As long as you do that, you will be able to keep up. But if you don't, then things will not go well. We will fall behind. Demeter asks, how do we join the office hour? The link to the office hour is on the Canvas page. So our main page in Canvas, the syllabus page, I can show you here really quick. Where is it? Here, here. So if you go to the home page on Canvas, there is a link, full syllabus, web assign, office hours. Click this link between 1 and 2 p.m. And you will join the office hour meeting. I have a waiting room set up there, so you won't be admitted right away. I have to let people in. That's so that people can talk about private things with me if they want to. Things like grades where you don't want to have that conversation in front of other people. But yeah, that's how you join. Any other questions? Alrighty then, I am going to sign out. If you would like to come by office hours, I'll see you there. Otherwise, you can reach out through Canvas messages or email. If we don't do any of those things, then I'll see you on Monday. Please remember to continue working hard on the homework.